we're continuing on today with very similar material to what we did last section, with one major change. But it's like the majority of these questions are the same questions that we just did. So most of you did fairly well on your test yesterday, so we will talk about this a little more today. So in the last section, most of the time we expressed our net force as applied force minus force of friction. The applied force was always in the direction of motion. Okay? The change that's going to happen today is that the applied force is not necessarily the only force that we're going to use to put it in the direction of motion. For example, if I took a look at somebody standing in an elevator, okay? If the elevator is at a standstill, that would mean that our net force would equal 0 newtons. Well, what's the first force acting on that elevator?
Gravity.
Force of gravity, working it straight down, right? So there has to be a force that's opposing it. That force is the cable. And we're going to refer to that force as our tension force. Okay? So in this case, our net force is the force of tension minus the force of gravity. Now I could rewrite that as force of gravity minus tension as well. And I'll talk about that in a minute. But what we know is if that elevator is at a standstill, then that means that my tension force is equivalent to my force of gravity. Right? Okay? So that's because the net force is 0. Now if this elevator is moving in a constant motion, going at a constant velocity, this still applies. Tension is equal to force of gravity. Because your net force is mass times acceleration. So if there's no acceleration in the question, then there's 0 net force on it. Okay? Now, if that same elevator is moving downwards, then my force of gravity must be greater than my tension force. So I rewrite it as force of gravity minus tension. So that's if the elevator is moving down with an acceleration. Okay? Then my force of gravity is the greater force, my tension force is the one holding it back. If it's moving upwards, my tension force is greater than my force of gravity. It's overcoming the force of gravity. Okay? So what we're looking at in this chapter that's different than the last chapter is, number one, we're going to deal with cables and strings a lot more. Okay? And the second thing is we're going to change our forces in the way we write them so that we always have the direction of motion being the greater one and the force of friction and the force of gravity holding it back. But the tension could also be the one that's holding it back. So it's always direction of motion minus anything opposing that motion. Okay?
Wait, so the second force, that tension, subtract the force of gravity that's going up
We're gonna, yes.
with acceleration?
Yes. Okay, so let's look at examples. I don't know what page it is because I didn't copy the pages very well. It's about 156. Sample problem. 75 kg man stands in an elevator. What will be the force the elevator exerts on him if the elevator is at rest? Okay, So again, I draw my free body diagram. He's 75 kilograms, all right? The elevator is at rest. So my force net is equal to 0. Therefore, my tension is equal to my force of gravity. So he's standing there and he'd be falling. But we're going to assume that the cable is what's holding him up. So therefore my tension is equal to my force of gravity. So if that's the case then, how much tension force is working on him? (75 kg) times your acceleration of gravity. So the amount of force acting on him then is what? 735 newtons. Okay? Pretty straightforward so far. Now, the elevator is moving upward with a uniform acceleration of 2 meters per second squared. Okay, so the net force on it then, it's moving up. So which is the greater force, tension or force of gravity? Tension. So I write it first, minus my force of gravity. Okay? This mass is 75 kg, and it's moving up at 2 meters per second squared. Force of gravity is still 75 by 9.8. So what's the tension in the cable now then? (150 plus 735), which is 885 newtons. Okay, so I just simply 75 times 2 is 150. Add the 735 to that side. The tension has to be greater. So if the elevator is moving up, I understand that the tension in the cable has to be greater than the force of gravity. So that's how I find out whether or not I got it right. Okay? The elevator is moving downward with a uniform acceleration of 2 meters per second squared. So now, this is the part that you're going to do a little bit different than what the book is going to show you. Most times I'm going to put the acceleration downward, usually is accelerating, and then upward is a negative. I'm just going to keep it as a positive now. What I'm going to switch is this here. This will make your life a lot easier. So again, it's moving down at 75 times 2. So now the book would probably make that a negative. I'm not going to. Now what's greater, the force of gravity or the tension if it's moving down? Force of gravity. So I'm going to go force of gravity minus my tension now. Force of gravity is the direction in which it's moving. So I've got 75 times 2 equals 75 times 9.8 minus my t. So now I'm going to subtract 150, subtract 735. So 150 minus 735, which is going to give me 585 negative. That's equal to my negative tension. So what's tension equal? 585 newtons. Should my force of tension be less than my force of gravity?
Yeah.
Yes, how come?
Because you're going down.
Because it's moving down. So that means that my force of gravity is greater than my tension.
So is our force of gravity always the mass times the amount of moment, like always? Yeah.
Its acceleration of gravity doesn't really change.
No, I just
So
know.
therefore, the force of gravity is mass times acceleration of gravity. Okay, so far? So the only difference from what we've done so far in this section than what we did in the last section is we had that tension. And that's it. Okay? Now, one of my favorite things to do is work with these questions on page 159. And that's pulleys. All right. So I have a mass set up right here. What's the mass on the table? 2 kg. 2 kg. And a hanging mass of 5 kg. All right. So, these questions here, again, the book is going to do this differently. Okay? So, it's not as easy to follow through the examples in the book if you're going to do it the way they are going to, because I'm going to show you how I'd like you to approach this differently, because it's going to make it a little easier on you, because you're going to do it consistently the same all the time. Alright? So I'm going to look at these two masses. They are connected by the same string. Okay? Now, I'm going to look at two things. The masses as a unit moving together, and then I'm going to look at the individual forces on each mass. Okay? So, if I'm looking at these forces, just looking at the diagram here, what force is going to move the two masses? Force of gravity on which one? On the 5 kg. So, if I let them go, the mass of the 5 kg is going to pull them. It's going to pull both of them. What's going to hold them back? What is it? If there's friction, on which one? The 2 kg. So the friction between this surface here and the 2 kg mass is going to hold them back. Alright? Now, if this was 2 kilograms, they may or may not move depending on how much the friction force is between the surface and the 2 kilogram mass. So the first thing that you do in every one of these questions, FNet again, just like we did last section. Again, put the direction of motion of the two as your lead force. So in this case, the force of gravity on the 5. Now, in this question, it's a smooth level table, therefore, there is no force of friction. So the only thing that's going to move these two masses is the force of gravity on the 5. So now it wants to find out what is the acceleration of each of these going to be. So mass times acceleration is equal to my force of gravity. So I write it out like that. How much mass is this force of gravity going to move?
7 kilograms.
7 kilograms. So I put that right here. because that force of gravity is going to pull both of them. They're attached, right? Force of gravity is 5 times 9.8. So what's the acceleration on them? 7 meters per second squared. Okay? All right. Does anybody have any questions about that? Again, this focus is on the two of them being attached to each other. It's the same as when we did the train question, or we had the question of the 3 kids lined up, or the question of the airplane and the 2 gliders. They're all the same. One mass is pulling the other 2 behind them. This mass is pulling the 1-2 kg with it, because they're all attached to the same string. Which then means that the tension in the string is the same on both masses. So now what I'm going to do, and again, this is not how the book does it. The book does the individual work first. I will show you what the book's doing, just so that you see it, but I don't suggest you use the method that they use. So now I'm going to look at the focus is on each individual mass now. So I'm going to redraw this. First things first. On my 2 kg, I now know how much it accelerates. So what are the forces acting on that 2 kg right now?
Force of friction and 5 force.
Okay, but there's no force of friction because it's a smooth surface.
Yes.
Okay? So what's moving the 2 kg? Don't look at the 5 right now, just look at the 2 kg. What is moving it? The string. And what do we call that force? Tension. And it's moving it to the right. Agreed? So there's my tension force. Now there are 2 other forces that act on it that we ignore. What are they? Force of gravity and normal force. That's right. Because they're not moving up or down because of the table. So we do add those in, but we ignore them because they cancel each other out. So then going back to this, if there's no force of friction, what's the net force equal to in this question? Tension. And that's it. Okay, there's nothing holding it back. Tension's moving that force. Okay? So now, I take the mass of it, just 2, and I times it by its acceleration. What's it accelerating at? 7. And that equals my tension. How much force is in the tension force? 14 newtons. Alright? So the only thing that can change in this question is if there's a frictional force. Other than that, it's not going to change. Okay? Now let's look at the 5 kilogram. If I have done this question correctly, the tension on the 5 kilogram should equal the tension on the 2 kilogram, because it's the same string attached to both masses. So let's check it and see. 5 kg. What's the forces acting on the 5 kg? Force of gravity pulling it down, and
Tension pulling it up.
tension pulling it up. Very good. Okay? Are there any horizontal forces? No. So then what's the net force acting on this guy then? Which direction is it moving?
Down.
Down. So what's greater, force of gravity or tension? Force of gravity. What's holding it back? Tension. Okay? So now I plug in the net force, 5 kg. What's it accelerating at? 7 equals 5 times 9.8 minus t. Negative t equals, so 5 times 7 is 35. 5 times 9.8 is 49. 35 subtract 49 is negative 14. Tension equals 14 newtons. You can guarantee that you get these 100% correct. You don't need to do this, but it just proved that I got the right tension. Okay? You can use either one of these to get your tension force.
Are we ever gonna deal with like a balloon, like with a string, where it's going up?
No.
Yeah.
What we're going to deal with, the hardest question is when we have an inclined slope and a mass on the inclined slope with a pulley on the other side. So we did the inclined slope last section, now we're going to add a pulley to it. Okay, but we don't need that yet. That's where we're going. Okay? So the first thing, if you recognize or you notice, what's the first thing that I do after my free body diagram? Write out my F-net equation every time. And then you have no issues. Okay? So the second type of equation dealing with pulleys is if I have two pulleys that are actually hanging and with different masses. So let's look at that example now. Okay? All right, let's look at the forces that are affecting the two of them. Again, thank you, Gary. Break this down. Okay? The two forces that are affecting it. What's going to move these two forces, these two masses? The gravity? Which direction is it going to go? Say again? The 3 kg is going to go down? So I have this force of gravity right here, right on the 3 kg. What's going to hold it back from moving? Okay, now I don't have tension yet because I'm looking at them as being two masses combined. That's right, Jake. Gravitational force on the 1.5. Okay? So does everybody understand that there? I'm ignoring the rope for a second. I'm just assuming, treating it as if the two masses are connected together, which they are, but they're moving. So clearly, the heavier mass is going to move the direction of this. So then what's my net force in this question? Net force is equal to, what's moving them? Gravity on which one? The 3. So the force of gravity on the 3, and what's holding it back? The force of gravity on the 1.5. Perfect. Okay. So both masses are now moving, right? So what's the combined mass? 4.5. A equals 3 times 9.8 minus 1.5 times 9.8. So I can get my acceleration of the two here. So 3 times 1.98 minus 1.5 times 9.8 divided by the combined mass, which is 4.5.
3.267.
3.627?
3.267.
267, thank you. So they're both moving at 3.267 meters per second squared. All right? Again, what's moving them? What's holding them back? That's all there is to it. Okay? Now, let's find our tension forces. So, to find the tension forces, I look at the individual masses to do that. So the first one, let's do the 1.5. Okay? 1.5 kilogram, you're looking at it. What are the two forces acting on it? Force of gravity. And what's pulling it up? Tension. What's the net force? Which direction is it moving? Tension first. And what's holding it back? Force of gravity. Okay? Go ahead.
Tension is not equal to force of gravity from
No. No. I'll show you why in a second. Okay? Let's look at the 3 kg force now. What's acting, or the mass? I see force, but it's mass. What's the 3 kg? Which way, what's the force is acting on it?
Gravity.
Gravity's pulling it down, right? And what's moving it up? Tension. The net force on this guy now, force of gravity subtract tension. Like that. Okay? So now, 1.5, what was the acceleration of this guy? 3.267 equals the tension minus force of gravity of it, which is 1.5 by 9.8. So calculate your tension. 1.5 times 3.267 add 1.5 times 9.8. Your question get answered? We get 601 newtons. Okay? So now, let's work with the 3 kg. So 3 times 3.267 equals 3 times 9.8 minus my tension. Minus tension. So 3 times 3.267, subtract 3 times 9.8. Work out to the same value, 599, pretty close. Okay? These two pulley questions are new to you. You haven't seen anything like this yet. The first 3 questions only works with force of friction, or no force of friction. Okay? All right. Okay. So, again, let's look at this again. You should be making notes on this. The first thing I do is find out the net force on the 2 objects moving together. So you started with the net force of the two. The greater mass force is always going to move it, subtracting whatever's holding it back. In this case, it's just force of gravity holding it back. Once I found my acceleration of the two moving together, I then individualize the masses to calculate what my tension is. All right? Okay? Now you haven't done too much yet, so I don't suppose does anybody want anything clarified or asked for now?
Second step, what did you do to that 4.5?
I divided it underneath here.
So you do, okay,
I got E by itself.
okay.
Okay?
And why did you take that answer? Oh, because of the floors.
Your force now is your total mass times our acceleration.
In this case, it was yes, because you're moving both of them.
Oh, I see.
But when you're looking at the individual masses, and it's not, it's just each one. Okay? All right. The next thing I'm going to show you, we've already talked about, except we didn't do much work with. And that's the coefficient of friction. So I mentioned this the other day. The force of friction can be found by taking the normal force times the coefficient of friction. If you look at the top of page 163, I think it is, it gives you different surfaces on a chart and what the coefficient of friction is. So if it doesn't tell you in the question, you go back to this chart and find it. Okay? So I'm going to look at one sample problem, then I'm done for today. Okay. Horizontal force of 50 newtons. Is required to pull an 8 kg block of aluminum at a uniform velocity across a horizontal wooden desk. And it wants to know what the coefficient of friction is. So to solve for coefficient of friction, I have to rearrange my equation. So what is the coefficient of friction going to be equal to? Just rearrange the equation.
Force, friction over force normal.
Thank you. Force friction over force normal. Okay? So, there's the first thing. The second thing is, let's draw ourselves a picture. What are the forces acting on this? Force applied. So say it's moving to the right, 50 newtons, right? That's force applied. Okay? What else is acting on it? Force of gravity is pulling it down. The force of gravity is 8 times 9.8. Do you want to punch that in?
78.4.
Okay. What else is acting on it? Normal force. And what does a normal force equal? Yeah. We're going to just leave it at 78.4. One of them would have to be a negative, I agree with you. They'd have to counteract each other. But all we'll do is we'll say they're in opposing directions. So what's the final force acting on this 8 kg box? Force of friction, which is what we're trying to find. So how do I find my force of friction? I'm missing something here. What am I missing in this question here?
They gave us our force. Yeah.
No, they didn't give it to us. How come it's 50 newtons? Read the question. Reread the question and tell me why it's 50 newtons. Say that again, Jake.
Uniform velocity.
Uniform velocity. Therefore, my net force is what? If I have no acceleration, what is it, Brittany? 0 newtons. Which means then my applied force is equal to my force of friction. So we go back to this. Net force equals applied minus my force of friction. My net force is 0. Therefore, my applied force is equal to my force of friction. So my force of friction then in this question is 50 newtons. My normal force is 78.4 newtons. Therefore, my coefficient of kinetic friction is 0.64. Now, because it's a coefficient, it doesn't carry units on it. The units canceled out. Newtons divided by newtons is 1. So there's no actual units on a coefficient. And if you remember from math, a coefficient is just the number that's in front of the variable. So it doesn't have units on it. So there it is. So the key to this question was right here, uniform velocity, meaning that you had 0 net force. All right? Questions 2 and 3 and 4 I'll go through with you tomorrow, if need be. They're the same questions we did in the last chapter. So you have 3 questions on page 158. Three more questions on page 161, I think. 3 pulley questions. And then there's 7 questions if you get done that. Page 165 and 166. Right?
Okay.